All right, so today we're going to solve this problem. Hopefully everybody has a copy of it. Otherwise, there's some extra copies up here. It's a problem that's due for the homework, so I thought that would help you. Water is the working fluid. Great. We don't have. You can have an organic Rankine cycle, meaning that you use a fluid that has carbon in it. But most of the time, it's water as a working fluid. It's an ideal regenerative Rankine cycle. Ideal meaning that it's reversible turbine, reversible pump. Reversible expansion through the turbines as well as pump. All right. It's regenerative. What does that mean? You're going to have a feed water heater. You're going to either have a closed or an open or both or multiple, but at least you're going to have one feed water heater. And it's our traditional Rankine cycle. Oh, they tell you you have one closed feed water heater. All right. Superheated vapor enters the turbine at 16 megapascal and 440 degrees C. Let me ask a question. After it comes out of the steam generator, what is its pressure and temperature? 16 megapascal, 440 degrees C. You have to kind of know where all the components are and what comes after the steam generator is the first turbine. They give you the information about the condenser pressure, 30 kilopascal. The cycle, again, has one closed feed water heater using the extraction steam at 1 megapascal. So think about 16 megapascal. 1 megapascal is where they extract it to feed the closed feed water heater, and then the condenser is at 30 kilopascal. 3 pressures so far. Condensate drains from the feed water heater as saturated liquid at 1 megapascal and is trapped. That's a funny word, trapped into the condenser. What do they mean by trapped? They have a steam trap, and they tell you where it goes after the steam trap. Where does it go? Into the condenser. The feed water leaves the heater at 16 megapascal. That's the high pressure, and at a temperature equal to the saturation temperature at 1 megapascal. Well, if you have your steam table, you can look up the saturation temperature at 1 megapascal. We'll do that. It tells you on the outlet of the closed feed water heater, they often tell you both the temperature and pressure of the fluid leaving, and then it's going to go toward the boiler or steam generator. So it's already at 16 megapascal when it leaves the feed water heater. It doesn't need any more boosting, no more pumps needed. And it has a high temperature equal to the saturation temperature at 1 megapascal. It then gives you the mass flow rate of the steam entering the first turbine to be 120 kilograms per second. We'll use that piece of information later in the problem. We can do a lot of work before we need that piece of information.
So is part of the steam, like after it leaves the turbine, going towards the feed water heater?
Yeah.
Okay.
Yeah. So what you need to do is make a sketch of the plant. And you've got to get the right plumbing and the layout. How many turbine stages? Where is this pump? How many pumps? How many this, that? Make a layout of the plant from this word problem, and then number the states, starting with state 1 being into the first turbine stage. Okay? So I'm going to pause. You need to do this by yourself. All right. So I was talking to a student after the 8:30 class. One of the things I'll stress again and again and again, the book, the book, the book, the book. Read it, open it, look at it. There's obviously some people in here who have been reading the book. They've been prepared. They know what's going on. Some others, it's like, if you open this book, you'll have a lot of questions answered. All right? So do that. Now, in the interest of time, I'm going to sketch it out kind of in a layout like the book has. They have a steam generator. Then out of the steam generator, they go into a turbine 1. After the turbine, they don't go back for reheat. I want to go back for reheat, but they don't do that. All they do is divert some down to the closed feed water heater, and they have to continue to a second turbine. Otherwise, the extraction pressure, which is 1 megapascal, can't be the same as the condenser pressure, which is 30 kilopascal. I know they're giving you a word problem, but they don't want to make it 500 words long or 1,000 words long, so they're being economical. But there is a second stage turbine, okay, or the second turbine, okay? All right, now after the condenser, you come out and you're going to have saturated liquid, put it into a pump. The pump is going to blow it right on through this feed water heater. It's a closed feed water heater. And they tell us about the pressure coming out here. Isn't it 16 megapascal, just like it's 16 megapascal up here? And they tell us the temperature coming out for that feed water. It's the saturation temperature at 1 atmosphere. Not 1 atmosphere, 1 megapascal. And that comes in at about 179.9 degrees C. That's that TSAT. So right away you know that you only need one pump. You don't need two pumps. And the extraction, the steam that's extracted, is going to collect as condensate in the bottom and come out. So that extraction steam is 1 megapascal. It's going to come out saturated liquid at 1 megapascal. You have to do something with it. You put it through a special device known as a steam trap. We talked about that last time. And then you dump it into the condenser. I'm going to redraw this condenser a little bit to help us in analysis. All right? The condenser has one outlet, but it really has an inlet right here, and for conceptual purposes, a second inlet right there. See that? I think that'll help us in analysis. Okay. Now, introduce states. So we'll put right here is state 1. This is state 2. Now, we introduce these states for unique pressures, unique temperatures, enthalpies, entropies of the working fluid. Even though the fluid splits there, it's the same steam that goes into the second turbine as well as goes down to feed that closed feed water heater. I don't have state 3 and then state 4. That makes no sense. They're all the same state right there. Okay, so clean that up a little bit. Okay. State 3 is what comes out of that second turbine. State 4 is the saturated liquid coming out of the condenser, and that feeds the pump. State 5 is what's after the pump. State 6, we kind of went all the way around the loop, but now we have to look at what happens to that condensate. So that's state 7. And this is, I'm going to put it way over here, state 8. So I have at a minimum 8 unique states, and these are my components. The next thing we do is we talk about fractions of flow. We know that certain percent of what went into the first turbine is diverted to feed the closed feed water heater. Well, let's put that as Y. Y in parentheses is a mass fraction. The notation used in the textbook about what's diverted. So what continues is 1 minus Y. What continues through 3 down to feed this condenser right here is 1 minus Y. Right? But it's 100% a 1 in parentheses, that's notation used in our textbook, for what feeds the first turbine. All right. Now, let's go down here. If it's Y on the shell side of this, then it's Y coming out as saturated liquid, going through the steam trap, which is then Y coming over here from state 8 and feeding the condenser. That's why I kind of put them both at the top, both feeding at the top of the condenser. So what is it at 4, the saturated liquid coming out? Is it Y or 1 minus Y or 100%? It's back to 100%. That takes a little bit to figure that out. And then it's 100% going through the pump and 100% coming out of that closed feed water heater ready to go into the steam generator. So we figure out all of our mass fractions. Yes, sir?
Could you explain why it didn't have a second pump again?
Because they tell me that this right here, the feed water leaves the heater at 16 megapascal. If they told me it came out at 8 megapascal, I need to get it up to 16. I have to put another pump in there. Yep. Okay. A lot of work in doing that, but you have to get that correct. Okay, once you do that, you want a table of properties, and then a table of energy transfers for each component. All right. Now, before we leave this, we're going to need to figure out how large Y is. Is it 16%, 18%, 22%? We can get the equation for Y based on knowing the H's, the enthalpies. You do this a few times and you know what the game is. So you do a control volume around that closed feed water heater. And you do a mass balance in terms of Y's and 1 minus Y's. It's trivial, right? But you do now an energy balance. Okay, now I'm going to do it a little quicker than probably you need to go a little slower the first time you do it. But an energy balance. It would be like the mass flow rate coming in from state 2 times the enthalpy from state 2. But then I'm going to divide that whole equation by the mass flow rate that went through the first turbine stage, and it boils down to the enthalpy coming in from state 2 times Y, which is a ratio of the mass flow rate coming down divided by the m dot total. All right. Then I'm going to have what else coming, actually going out will be the enthalpy at 7 times Y, kind of in minus and out. And then I could have another in, which is H5 times 1 minus an out H6 times 1, all equal to 0, the sum. Okay, you now do a little rearranging and you get the equation for Y. H6 minus H5 divided by H2 minus H7. Thank you very much. Okay, now we need to get properties. You'd use your tables to get the properties. What I'm going to show you is a piece of software. I mentioned it before. REFPROP, you just Google the name, you'll get to it. If you type in mini in front of it, it'll take you to this website, mini REFPROP. You can see that it's for students. It's a free sample version. It has water, carbon dioxide, refrigerant, nitrogen. It has quite a few things in it. But the only thing we're interested in is water for this problem. And then you download and put it on your machine and run it. So when I have it on my machine, I'll have a little go-to start it. I started it up, and we're ready to start executing. All right, so under File, you can do some things. Let's not worry about that. Under Edit, you can do some things. Let's not worry about that. Options. Options are units. So you can select, do I want to work in temperature in degrees C, temperature in Kelvin, Fahrenheit, Rankine? We're going to use C. You can work pressure, pressure in megapascal, bar, ATM, millimeters of mercury, a lot of choices. It's like good software. It should allow you to work in the units you want. Volume in meter cubed, you can change it, mass in kilograms or pound mass, etc. Let's leave it in kilogram. Okay. So you can explore some of these. They have viscosity, thermal conductivity, surface tension, more than we need. All right. So we just click OK. Then also, you can talk about your reference state. Sometimes somebody will say, well, how come the value of the enthalpy from this software doesn't agree with the enthalpy for out of the table? Often you trace it to the starting point for your energy measurements. Go back to Chapter 3. Go back and look at that discussion, because that was a big discussion about energy measurements all have a reference point. They start. Refrigerants, they like to have the saturated liquid at negative 40 degrees C to have an enthalpy of 0. For water, they commonly pick the internal energy at the triple point for the saturated liquid to be 0. The internal energy, not enthalpy, at the triple point around 0.1 degrees C as a triple point. And so you just have to be careful. Nitrogen and other gases, who knows? Take a look at what they do. But we're not going to change it. We're going to stay with this. But that's a often I'll get questions like that. Okay, let me go back. Options. Properties. There's a lot of properties. If I cared about the mass density, check the box. If I don't check the box. If I care about the specific heat constant volume, check the box. If I don't care about entropy, check it. You know what I'm saying? There's a list. Joule-Thomson coefficient. There's too many. Speed of sound. Gibbs and heat of vaporization. But let's do this. We're going to check quality. We're going to check entropy, enthalpy, specific volume. They didn't spell it out, but that's what they mean by volume. Temperature and pressure. All right. Now, you can go and get more properties. Thermal conductivity, viscosity, kinematic viscosity, all these. You can get derivatives of properties. You can get special properties, and if you're really interested in, flow exergy would make sense if we were doing an exergetic analysis. Yeah, pretty nice, huh? Flow exergy, boom, there it is in another column. But let's not do that. But let's jump back, and these are the only ones I'm really interested in. Say, okay, now let's see if there's any other options. Not really. Property order, I like to put pressure first, then temperature in a table. If you wanted to move it up, put temperature first, then pressure, fine. But I like to put pressure first, then temperature, then quality, then specific volume, then I'm not putting volume in there. No, I am, specific volume. Density I'm not putting in. Internal energy I'm not putting in. Enthalpy and entropy. This will give me the right column that how they line up in my table. Otherwise, you can change that order. All right, we pick our substance. Well, it's a pure substance. They do have mixtures and all kinds of crazy stuff. Let's not do that. Let's just go look at, well, there's a lot of substances I have on here. You'll only have the minimum, right? Water and a refrigerant here or there. But, okay, there's water. It's now picked as my substance. Now, I can do some calculation. I can calculate it at specific states, and we're going to do that. Or I can just even do a plot. I can plot the temperature entropy diagram. Boom, I'm going to plot the temperature entropy diagram. I played with this a little bit. I'm going to just do this. I'm going to put one line at 30 kilopascal. In 30 kilopascal, and just put 100 here or some ridiculous. And then I'm going to put it at 1,000 kilopascal. And what was my other one? It was 16,000, right? 16 megapascal. All these are pressures in kilopascal that I put. And then the entropy range looks good, 0 to 10. Temperature, 0 to 600. Maybe if I want it 0 to 700, I can do that. And I can connect. This is a little box. Somebody asked me about it earlier. Connect the saturation states. So it'll draw a horizontal line from saturated liquid to saturated vapor in the dome. There you go. So that looks pretty good. And then you say I would like to maybe modify my plot. Well, guess what? Okay, I can do this. Modify plot. And maybe the saturated liquids I want to color blue or darker blue. And maybe I like a thicker line. I don't know. Just apply it. Then the saturated vapor, maybe I want to put it red with a thicker line. Apply it. Maybe these I want to put blue. I like blue for those. Leave them thin. Blue. I'm not that efficient. I'm just showing you some options to make it look good. I don't think I hit apply for these, so it didn't accept it. Okay, hit apply after you make your selection, then plot it. There you go. Okay, so you can make a little plot. Probably change the size of the fonts to read them. This is almost unreadable, right? They're so small. All right, but now let's go back and we want to calculate at specified state points. So why not use our same state numbering system 1? What was my pressure? 16 megapascal. If I hit return, it doesn't fill the rest of the table in, but from chapter 3 or 2, whatever, 2 intensive properties fix the state. So if I tell it the temperature, 440, when I hit return, it's like, bingo. Use this to check your work, not do your work. I still want to see your hand calcs. I know it can be really trivial, so show me you could do at least one double interpolation. If you've got an unfortunate draw of numbers in the random drawing where you have 5 or 6 double interpolations, well then show me at least you can do one and then use the software. You can use IT. You need to show me at least one by hand. And then you can use IT, REFPROP, some other software. All right. It now goes down to 1,000, true? But what was it? What is constant through that first turbine? Temperature or entropy? Well, I'm going to put my cursor up in that box. I'll copy it. I'll move it down here. I'll do paste. And then it shows me the quality. It shows me the enthalpy. Hey, engineers aren't all dumb. They invested some good effort to make good software, right? This helps you. Now, what about state 3? What is the pressure? 30 kilopascal. It goes through the same, copy that entropy, paste it, fills it out. All right, now, what comes out after, what's state 4? Saturated liquid at the 30 kilopascal. So what should I put? 30? Put quality, very smart. Quality 0. Bingo. All right, it goes through the pump. This is something different than your hand calculations. In the software, you can handle constant S through the pump. What comes out of the pump, state 5, it's 16 megapascal, isn't it? But I don't have to do V times dP. Hand calculations, that's the way you do it. But here, just grab that S, copy, put it down here, paste. Isn't it isentropic to the ideal pump? Now, if you have a real pump with an efficiency, you're going to have to make some hand calculations and do this. But for this problem, it's really easy in the software. You're going to have to be doing hand calculations and jumping back and forth between the software if you have an isentropic efficiency for the turbine, isentropic efficiency for the pump. Yes, sir?
For the quality, could you type in superheated and it'll register that?
Well, you put 0 to 1. It really doesn't make sense to go outside that range. So if you put in a quality of 1.2, it's probably going to barf and say, hey, you're confused. It won't let you do that. All right. What about state 6? Didn't they say it was that high pressure? But what was the temperature? It was the saturation temperature. Well, I look it up and type it in, or I just realize, hey, I got it right there. Isn't it the temperature at state 2? So I just go up, copy it from state 2, bring it down and paste, and then there you go. Almost too easy. That's pretty hard to do this in your tables. State 6 would be hard. Okay, now state 7, saturated liquid coming out the bottom of the closed feed water heater. What was the pressure again? 1,000. It's right before it gets to the trap. And it's saturated liquid, put in 0, boom. All right. Now the hard one, state 8. That's after the steam trap. What is the pressure at state 8? It's after the steam trap. The steam trap drops the pressure. Look at the symbol of the steam trap. It's like a valve with a circle on it. It's 30 because it dumps into the condenser at 30. So it's 30 kilopascal. But what is, what's the second property? Quality is 0. I'm going to pause, walk around. What is the next property for state 8? All right, so a lot of you got it, but why do I copy down H? Why? It's a valve. It's not isothermal. Look at the temperature difference. It went from 180 to what? About 70. How can you drop temperature just by going through a valve? Because it takes a lot of energy to break those intermolecular bonds that keep it a liquid. It drops it to a low pressure. It wants to go into a gas. It says you can go into a gas, but not for free. Where are you going to get that energy? I'm going to get it from my neighbor. And so kind of the vapor that's higher energy state, look at Hg compared to Hf. Some of it flashes, what they say. What is the quality? 20%. What does that mean? How much by mass is now in the vapor state at state 8? Hold it. It's 20% by mass is in the vapor state. 80% by mass is in the liquid state. So what I'm going to do is I'm going to grab this whole table, if I can. I'll try that again. I think that's grabbing the whole table. And I'm going to move to another favorite software of mine. And I'm going to paste it right here. And those are actual values. And what did we do all the work for to get the H's, didn't we? Didn't we really want to get all the H's? Yeah. So now I remember my equation for the fraction that's diverted. Hey, did I write it correctly here? Good. So now I'm going to implement it. I'm going to say give me H6. I'll come over here. There's H6 minus H5 right there. Close parent, underline, and then open parent H2. That's right there. Minus H7 right there. Close. And that's the fraction. I grabbed H8 by mistake. Oh, they're the same. So I'm still good. Okay. Well, we're good. Well, it says H for the column, but I'm thinking the enthalpy at state 7, so it's a little confusing, the notation. But 26% is diverted. So what continues on, I like to put 1 minus. I know this is a trivial step, but I like to do it. There you go, 73.7% continues to the second turbine. Now that I have all my properties, I could come over here and for each component, let's do it. Turbine 1, turbine 2. Then after the second turbine, I'll go to the condenser. Now the condenser is a little tricky, so let's go back to our illustration. And I'm going to break the condenser, that's why I wrote it like this, as if there's 2 condensers. One handling this stream and one handling this stream. Why? Because the mass fractions or the mass flow rates are a little different, and I can make an error here so easy, right? So I'm going to talk about the condenser going from 3 to 4 as well as 8 to 4. So let's go back to the Excel. I'm not going to try and do the condenser all at once. I'm going to do the condenser, I can say 3 to 4, 8 to 4. There's somebody in the back, they have their laptop open, they've downloaded, they're running this software. Smart. You want to do that too? You can do that, right? Or you pay attention. Either one, whatever works for you to get the most out of this lecture. Let's continue. I have a pump. Do I need to put in the feed water heater? Well, there's no energy transfers with the surroundings, so I really don't need to put the feed water heater in. How about the steam trap? It's a component, but there's no energy transfers with the surroundings, hence I don't need to put it in. But I need the steam generator to put in. All right, so I think that's the minimum, the subset. And I have to reduce, I think, the font size or something here to make it fit on one screen. Sorry, I tried to make it as large as possible, but now somebody visited me from the 8:30 class, and we talked and talked and talked, and he convinced me, oh, I need another column. I've taught this class, I don't know how many times. I've shown students how to do this, I don't know how many times, but the student said, hey, and so in the discussion, I now recommend adding a column, which is the mass fraction column. So for the turbine 1, what is the mass flow rate going into turbine 1 compared to the mass flow rate going into turbine 1? 1. Isn't that nice? So maybe I'll even do this to make it easy to read. I'll put it in the middle like that. All right. How about what's going into the second turbine, the mass flow rate into the second turbine divided by what went into the first turbine? That's 1 minus y, which I just calculated right there. Why not tabulate those for each component so we reduce the errors? You can make so many errors in engineering. You want to reduce your errors. So how about from the condenser 3 to 4? Oh, wasn't that the 1 minus y? Yeah. But the condenser from 8 to 4, that other side of the condenser is Y. Okay, pump, they're back to 1. Yeah, and the steam generator, back to 1. Now, I didn't do that before. This is the first time I did it. Now I do the Q's. For every kilogram going through the first turbine, what is the Q? Well, that's 0, 0. So let me skip it over due to the work, right? So for the first turbine, isn't that my H1 minus my H2? Sure. Hit return. 572.4 kilojoules per kilogram. And then I do it for the second turbine. I'm doing it not for the second column, just do it W without the W asterisk. It'll be H2 minus H3. Enter. But now I want to use this mass flow rate. So it's equal to what is here times right there. And it says, well, that didn't do much for me. But for the next one, it does, because for every kilogram that goes through the first turbine, I get only 366.9 kilojoules of work out of the second turbine. Make sense? Good. Now let's jump over to the boiler. What goes through from 3 to 4, and if we want it to have the right sign, you can either add the negative sign or whatever, but you know it needs to be negative when we do the sum. So H4 minus H3. And then 8 to 4 will be H4 minus H8. There. And now, to get the Q asterisk, I multiply by, hey, this doesn't look so good. Put that as percentages there. Maybe add another. There you go. Okay. Is equal to this times that mass fraction. And then this is equal to this quantity times that mass fraction. Now, those Q asterisks and W asterisks are all on the same mass flow rate basis. Okay. How about the pump? Well, it's only a work, and it's equal to this it's H4, that's right. H4 minus H5, thank you very much. At around 16.3 kilojoules per kilogram. Now at this point, somebody might say, I really fell in love with this VDP. Let's see how close VDP is compared to the 16.3. Make sense? So how about if I just put right here, V times dP. All right. I have, where's my specific volume? Isn't that my specific volume at state 4? And I multiply it by the change in pressure. It takes it all the way to 16 megapascal. And it's starting at 30 kilopascal. And Professor, this stuff doesn't work, this thermodynamics. It should give me 6, 7, 8 digits of, no, this is really good. Isn't it good? 16.32 versus 16.3. Okay, expand this one, see if they agree to another digit. Okay, well, they don't, but they agree to 3 significant digits. Good enough. All right? Right? Now, which one would I lay my money down as the most of the most of the most accurate? The REFPROP. Yeah, I mean, it's approximation. We assume the specific volume stays constant. Does the specific volume really stay constant through the pump? Well, it does the 3 significant digits, but not the 4. See that? And definitely not the 5. So that approximation is the V stays constant through the pump, and water is slightly compressible. Okay, slightly compressible. It's still a great approximation. On an exam, use VDP. You won't have access to REFPROP or any other software. Okay, let's continue on. This is still a 1-to-1, so I'm just going to copy that over. What about the steam generator? It's a add, and it goes H1 on the outlet minus H6, I believe, is the inlet, isn't it? And then this is a 1-to-1, so there you go. Now we're going to do a sum right here, S-U-M. Don't sum the Q, sum the Q asterisk. sum this column, right? And it will give us 923.0. Copy that, flame it over here, paste. And this one is the sum of the work asterisks. Again, when I'm doing my work, I want to check it to see if maybe I made an error. This is where I would stop, pause, go back and look for an error. If the sum of the Q asterisks on the same per unit mass basis doesn't match the W. Okay. Now, what does it say for the part A? What are they asking us to solve for? What is that net power developed in kilowatts? I gave you the handout. On the handout gives you the answer. I want you to spend a few minutes and show me when I walk around that you can get it from these numbers on the screen. Answer part A now. So we remember that this problem had the mass flow rate, m dot, going into the first turbine, T1, was 120, and I like to maybe do it kilograms per second. Okay, and what are we asked to solve for? We're asked to solve for W net, or W dot net, in what units? Kilowatts. Hey, what is a kilowatt? Is it a kilojoule per second? Yes. You bet it is. And so why don't I just take the mass flow rate times, whoops, I need to put that 120 there. Come on now. Leave that alone. Just escape there. Come right here and say equal to the mass flow rate times the specific work net. Isn't that it? Sure. That's the answer for part A. Part B is what is the rate of heat transfer to the steam passing through the boiler? That would be like Q steam generator in units of kilowatt. How do I calculate that? Do this mass flow rate times this. No, that's going to be ridiculous. That would be an error. What is it times? You're putting it into the steam generator, right? Isn't this what you're putting in? Yeah, that's what you're putting in. So you go, 280,000 kilowatts. All right. The part C asks, what is the percent thermal efficiency? Thermal efficiency percentage. Would it be as easy as the ratio of, this is the numerator divided by the heat in to the steam generator? And it comes in at 39.5%. Look good? The last part, part D, I left a little room right here to do some intermediate calculations. It's tricky wording, so let me pause and let you digest what they're asking you to solve for. They're asking you to solve for the mass flow rate of the cooling water that goes to the condenser. So let me jump back to the sketch. Here's my sketch. The way these work is they get some water out of a lake, they pass it through, and they return it to the lake. That's called the cooling water. It's lake water, river water, ocean water. Okay, that water experiences a temperature increase when it goes there. And in this problem, the temperature increase is 18 degrees C, isn't it? So maybe it comes in 20 degrees C. What does it go out at if there's 18 degrees C temperature increase? 38. Fish are not going to be happy. That's a big increase in temperature. If you ever fished around a power plant with the outlet, the warm water is usually not good unless you're in the middle of winter. Then the ice stays melted in that vicinity, and actually the fishing is better in that area. It's still cold water, but anyway, anybody a fisherman know this, relate to this? Yeah, fish love cold water. They suffocate in hot water. So anyway, if you put out too much hot water in a lake, it's bad for the fish. Okay, so they want to calculate that mass flow rate of that water. Well, what you typically do is break it into steps. What is the Q dot that has to be rejected in the condenser? Can you calculate that? What is the Q dot rejected in the condenser? Let's jump back to my Excel sheet. So maybe I say, what is the Q dot jet in the condenser? Okay. There's a couple ways you could do it, but would it be, hey, all this energy that came in minus what went out in work? Where else is do a global energy balance for the plant? I got some coming in the boiler. Energy either goes out the network, out the shaft to drive the generator, make electricity, or I got to reject some to the environment. Isn't that it in kilowatts? Isn't that nearly 60% of what came in? That's another way of calculating it. You could say 1 minus the efficiency times what came in. Okay, don't like percentages. Get rid of that percentage. Go back to a number and then shorten it a little bit. There, isn't that the same? There's a couple ways to make this calculation. But you find out what's getting dumped into the cooling water. And then you have to remember the equation for how that cooling water responds. So if I have the flow into the cooling water, the mass flow rate of the cooling water, the specific heat of the cooling water, the temperature rise of the cooling water, I could put CW, CW, CW on all that. Does that equation make sense? They told me that this is 18. I was able to calculate this from the problem given in the information. They want me to calculate the mass flow rate. I have one equation. The only thing I really don't know yet is the specific heat of the cooling water. I'm going to pause and let you think about it, and you give me the specific heat of the cooling water. All right, I have to rush a little bit, but 4.18 kilojoules per kilogram Kelvin. Where did that come out of? What table in appendix? It's near the back, A19. It talks about specific heats of common liquids and solids. Water is a common liquid. It's just a number, right? So it's good to know this. It's like somebody said, and this is a new clicker question, and I don't have clicker running today. Sorry about that. Insert new page. Somebody says, I look up specific heat, and it's 4.18 kilojoules per kilogram Kelvin. But I'm looking at my equation. I'm going to do this. I'm going to have this Q dot in kilowatts, units, is equal to the mass flow rate. I want that in kilograms per second. And I have this specific heat. I multiply by temperature difference. Hey, that was 18 degrees C temperature difference. They put in the specific heat. They say, oh, that's a kilojoules per kilogram Kelvin. Okay, I have a problem. I want you to convert this specific heat for the cooling water to give you the specific heat of the cooling water in units of kilojoules per kilogram degree C, because I want to cancel the temperature. I want you to do it by yourself. I don't want you to shout it out. And I want you to raise your hand orderly and call me over and I check it, okay? I want you to make that conversion. You see what I'm asking you? There's a figure in chapter 1 of the book you need to go and review and really say there's something important in this figure in the textbook, chapter 1. And it has 4 temperature scales like this. 2 are relative, degree C and degree F. 2 are absolute, Kelvin and degree R. They talk about where water freezes. 0 on that scale, 32 on that scale. Where water boils at 1 atm, 100 on that scale, 212 on that scale. The temperature increments are 100 between the same hot and cold. The temperature increments are 180 between the same hot and cold. To move from this one to that one, they say, hey, if you're given a temperature in degrees C, a number, just add 273.15, and you will get the right temperature in Kelvin. An equation like that is in chapter 1. Similarly, to go from degree F to R, 460. But one of the things they'll do, they'll say something like this. 1 degree C equal 1 K. Certain circumstances, it's absolutely correct. because they're now talking about a change in the temperature. Whoops. Where did I go? A change in the temperature. Isn't a temperature change in degrees C exactly the same as a temperature change in degrees, or leave that off on Kelvin. Nope.
We're all adults here,
That's new. Okay, I gotta compose myself here. It's just like 1 degree C is equivalent to 1.8. That's right, 1.8 degrees F change. Because there's 180 of these for the same scale, like a ladder with 100 steps versus 180 steps. So you need to have a temperature change of almost 2 degrees F to be the same as a 1 degree C change. But anyway, this is the big one right here. So when you're talking about a temperature change, you can just substitute degree C, because 1 degree C temperature change is equal to, don't try and fiddle with 273 in that equation. So this is 4.18. Thank you for those that got it correct. Revisit me and we'll try and do it next semester again. All right, because this is a hard concept. All right, I need to press on. So we come back to the analysis to finish it out in Excel. And the last thing was what's that mass flow rate, m dot, of the cooling water? And so you just figured out what is dumped in the condenser equal to what's dumped in the condenser divided by the specific heat, 4.18, divided by the temperature change, what was it, 18?
Yes.
18. And there you go, clean up the units, digits there. And this is in kilograms per second. So that's your answer to part A, B, C, and D for this problem. Before we end, I want to do something else. I want to go back to this REFPROP. Did we not have a table or an illustration here? True? You can come back here and say, I want to go to this plot, and I want to overlay this plot with something. What do I want to overlay it with? Well, why don't we overlay it with these? But let's put symbols that are round and red. Where's red? Red. And what did it just show me? Yeah, that's not bad, is it? So I did this before class. Let me jump back here. I mean, you're doing it. You can do it in the software. And here I didn't connect the lines, but what state is that? What is state at that 1 megapascal? 2, 3. Then you went over here to 4. You went through the pump. Where is state 5? Zoom in. Right? Zoom in. Or maybe this is the zoom in. Either one. No, this was the zoom in for the pump. So there's 4 and there's 5. So back on this one, there's 5 right there. Okay. Now, we had saturated liquid at the 16 megapascal. That's state 6. It's right on top of state 7. So that was the second zoom in. This is at that high pressure, 16 megapascal. This is the saturated liquid going out at the bottom of the closed feed water heater. The hard one to put on a TS diagram is after the steam trap. After the steam trap, it's state 8 right there. It's kind of a crazy one. Look at, if I draw a straight line up and down, isn't state 8 a little higher S than state 7? Remember, we had our steam trap like this. We had state 7 going in, state 8 going out. It dropped the pressure down to 30 kilopascal. What did it do to the temperature? Dropped it significantly. And the quality, you know, it went from saturated liquid, now it's some two-phase mixture. What did we say? It was around 20% quality? Yeah. So So state 8 is a hard one to put on there, but that's where it is on the TS diagram. Okay, thank you for letting me rush through this. I have a few minutes, so let me use the time wisely, answer your questions. Do you have any questions for me? One question, yes, sir. Go ahead.
At state 3,
Right.
how would you degree cells?
State 3, this one, you know it's a quality right there. And so once you know it, it's the saturation temperature at that pressure.
So you just basically just look at it.
Yeah, it's a saturation temperature at that pressure. I'll be in my office if you have any questions. Thank you very much.